The Western Front in 1915 wasn't just killing men. It was breaking armies in ways no one had prepared for. By spring, Britain had poured nearly 1.5 million soldiers into France and Belgium. Feeding them was hard. Supplying them was harder. But housing them, that problem was quietly becoming catastrophic. At first, the army relied on the obvious answers. Farmhouses were seized. Villages were stripped bare. Wooden barracks went up wherever space allowed. For a brief moment, it worked. Then German artillery rewrote the rules. One shell could erase a stone building in seconds. Wooden huts didn't collapse, they exploded, spraying lethal splinters in every direction. Each morning, staff officers counted the damage. More buildings gone. More men sleeping in the open. More sickness spreading through exhausted units. And the crisis wasn't limited to the trenches. Behind the front lines, massive logistic zones housed rotating troops, supply depots, and medical units. These areas should have been safe. Instead, they became fragile targets. Britain's army was expanding faster than its infrastructure could follow. Kitchener's volunteers kept coming, but there was nowhere to put them. Traditional construction failed every test. Brick buildings were too slow. Concrete bunkers were too expensive. Wood-consumed timber needed elsewhere. Canvas rotted in rain and cold. The winter of 1914 had already exposed the cost. Men survived bullets only to die from pneumonia. Medical reports were brutal reading. In some areas, exposure killed faster than the enemy. The War Office faced an impossible equation. Shelter hundreds of thousands of men. Build it fast. Ship it cheaply. And make it survive modern war. Nothing fit. What they needed wasn't a better building. They needed a completely different idea. That idea came from a man who wasn't an architect at all. Peter Norman Nissen was a mining engineer. Born in America, raised in Canada, trained underground, not in drawing rooms or design offices. When war broke out, he joined the Royal Engineers, bringing with him something rare, a deep understanding of how materials behave under pressure. In early 1916, Nissen watched supply depots being destroyed. And he noticed something strange. Brick walls collapsed. Wooden crates vanished. But twisted sheets of corrugated metal often remained, bent, scarred, but intact. Even more interesting, the curved sections were stronger than the flat ones. To most observers, this meant nothing. To a mining engineer, it meant everything. Nissen understood arches. Underground tunnels survived because pressure flowed around them, not through them. Flat surfaces absorbed force. Curves redirected it. During a quiet moment in March 1916, he sketched a radical idea. No frame. No beams. No skilled labor. Just corrugated steel sheets, curved into a half circle, bolted together into a continuous shell. Timber ends. One door. It looked ridiculous. Like a tin can cut in half. But the geometry was brilliant. The curved surface wouldn't resist explosions, it would deflect them. Blast waves wouldn't strike head-on, they'd slide across the surface, shedding energy as they moved. And the continuous curve meant every impact force spread through the entire structure instead of tearing one panel apart. When Nissen presented the design, the army didn't laugh. They were too desperate. Within weeks, a prototype stood ready. 3 men assembled it in under 6 hours. Officers doubted it would survive a strong wind. Then they tested it with explosives. A charge detonated just 20 feet away, close enough to obliterate a wooden hut. Dirt flew. Shock waves rolled across the ground. When the smoke cleared, the structure was still standing. Barely scratched. The secret wasn't thickness. It wasn't weight. It was physics. Flat walls take force directly. Curved surfaces turn it sideways. And the corrugations multiplied strength even further. Each ridge acted like a tiny structural beam, resisting bending from every direction at once. A flat sheet flexes. A corrugated curve fights back. What Nissen had built wasn't just a shelter. It was a lesson in how geometry could outsmart firepower. What gave the structure its strength wasn't thickness. It was geometry. Those ridges and valleys in the steel didn't just stiffen the metal, they forced force to take the long way around. Impact energy couldn't rip through a single flat surface. It had to fight its way across peak after peak, trough after trough, bleeding power at every step until very little remained. Just as important, the design erased the weak points that killed conventional buildings. No corners, no roof joints, no beam connections waiting to fail. From one side of the ground, over the crown, and back down again, the hut was a single continuous curve. Later analysis revealed something remarkable. The structure was flexible enough to absorb blast pressure without cracking, yet rigid enough to hold its shape under repeated punishment. That balance was almost unheard of. The real test came in the summer of 1916, during the Somme. Nissen huts stopped being experiments and became necessities. They appeared behind the lines as depots, aid stations, and troop quarters. And then German artillery found them. Near Albert, a supply hut was struck by a 5.9-inch shell, the kind designed to smash through concrete. It hit the curved roof at an angle, glanced off, and detonated harmlessly in a nearby field. Inside, terrified clerks braced for death, then stood up with nothing worse than ringing ears. The hut wore a dent. That was it. This wasn't luck. Reports poured in. A medical station survived 3 near misses that left craters big enough to swallow horses. An ammunition hut was peppered with shrapnel yet stayed standing. Troops described bombardments that sounded like being trapped inside a drum, terrifying but survivable. The physics ran deeper than deflection. Artillery shells relied on sudden resistance to trigger their fuses. Brick walls gave them exactly that. Corrugated steel did not. Many shells struck the curved surface, felt too little resistance, slid away, and detonated elsewhere, or didn't detonate at all. Even when explosions occurred nearby, the damage behaved differently. Brick buildings collapsed inward, turning debris into weapons. The Nissen hut had nowhere to collapse. Punch a hole in one section and the rest of the curve remained stable. The numbers told the story. In one sector, wooden barracks suffered catastrophic losses, over 70% casualties. Nearby Nissen huts, under the same bombardment, reported barely 12%, mostly men caught outside when the shelling began. By autumn 1916, the debate was over. The War Office ordered them by the thousands. Mass production revealed another quiet miracle. Nothing about the hut required special factories. Corrugated steel was already being rolled for farms and warehouses. Mills simply adjusted the curves. Standard bolts held everything together. Timber ends came from ordinary sawmills. This wasn't precision engineering. It was industrial common sense. By 1917, Britain was producing over 10,000 huts a month. Kits flowed from Sheffield steel mills, Scottish timber yards, and Midlands hardware shops to ports, then across the channel. Assembly was brutally simple. 4 soldiers, a few spanners, 4 hours. No skilled labor required. Divisions could arrive in a new sector and be housed before nightfall. Hospitals could be operational the same day. Shelter stopped being a limiting factor in warfare. By war's end, over 20,000 Nissen huts dotted France. Planners assumed they'd vanish with peace. They were wrong. When war returned in 1939, Britain faced the same problem, only worse. Now bombs fell from the sky. Cities burned. Civilians needed shelter as desperately as soldiers. During the Blitz, Nissen huts stood in the heart of bombed districts, storage depots, first aid posts, emergency housing. Time and again, brick buildings vanished while curved steel huts remained. In Silvertown, a 500-pound bomb obliterated a warehouse. The nearby Nissen hut lost doors, windows, and skin, but stayed upright. 2 days later, it was back in use. Airfields saw the same pattern. Reconnaissance photos showed shattered hangars and intact rows of huts. Naval bases used them along exposed coasts where wind, salt, and bombs destroyed conventional structures. By D-Day, they crossed into Europe again, housing troops, storing fuel, serving as command posts. 2 wars tried to erase them. They endured. When peace finally came in 1945, Britain faced a new crisis. Housing. Millions of homes destroyed. Schools gone. Communities shattered. The solution was already standing. Nissen huts, once dismissed as temporary, became classrooms, churches, halls, and homes. Children learned arithmetic beneath curved steel roofs built for war. Congregations prayed in structures that had survived artillery and bombs. Some were meant to last 10 years. Many are still standing today. And that raises an uncomfortable question. If a structure designed in desperation could survive 2 world wars, what else had we underestimated? What no one expected was how well these structures adapted to peace. The curved interiors, with their strange but effective acoustics, proved surprisingly suited to human use. Emergency churches became permanent. Communities settled in. In Maidstone, St. Michael's congregation worshipped inside a Nissen hut for nearly 3 decades. In rural towns, similar steel shells outlived the brick buildings they were meant to replace. Housing followed the same path. Entire estates rose from curved steel. Engineers divided interiors into bedrooms, added kitchens and bathrooms, and packed insulation into walls that were never meant to hold warmth. Families moved in expecting a brief stay. Many remained for 20 years. The word temporary became a bitter joke for people who raised children and retired beneath corrugated arches. Yet the huts endured. Sports clubs turned them into locker rooms. Factories used them as workshops. Farms transformed them into barns and grain stores. The structure didn't care what role it served, only what loads it carried. Britain wasn't alone. Surplus huts spread across the Commonwealth. Australia used them in remote settlements. New Zealand built rural schools from them. South African mines adopted them. Canada deployed them where conventional construction was impossible. By the 1950s, Nissen huts stood on nearly every continent. Even Antarctica nearly joined the list. The Americans had observed all of this with interest and regret. When the United States entered World War II, it faced the same shelter crisis Britain once had. In 1942, naval engineers unveiled their answer, the Quonset hut. The resemblance was unmistakable. Semicircular steel. Rapid assembly. Minimal skill required. America refined the idea. Steel-framed ends, integrated floors, altered corrugations, and mass-produced them on an industrial scale. Over 160,000 were built. They appeared everywhere U.S. forces went. But soldiers noticed something unexpected. Many preferred the original. The American version was heavier, slower to erect, and harder to transport. That extra strength on paper came at a cost in the field. The Nissen hut was lighter, faster, and easier to repair under fire. Its circular corrugations shed water better. Its flexibility reduced catastrophic collapse. Reports from Burma, the Pacific Islands, and Europe quietly confirmed it. The Quonset worked. But Nissen's geometry worked better. Production of true Nissen huts ended in the early 1950s. The idea did not. Modern emergency shelters still follow the same principles sketched during a tea break in 1916. Curved profiles. Corrugated strength. Minimal parts. Rapid assembly by untrained hands. Refugee shelters from Syria to South Sudan use evolved versions of the same logic. Disaster relief teams deploy curved steel structures after earthquakes, hurricanes, and wars. NATO forces still rely on updated variants for forward bases. The silhouette never changed. Farmers still use them. Engineers still study them. Architects still borrow their geometry. Temporary Olympic venues, festival stages, modular buildings, all echo the same curve. Some original huts remain, quietly defying time. At Eden Camp in North Yorkshire, visitors walk through functioning World War II Nissen huts more than 80 years old. They are not monuments. They still work. Structural engineers continue to cite the design as a masterclass in efficiency, maximum strength from minimum material. Even with modern composites and advanced modeling, matching that ratio remains difficult. Peter Norman Nissen never lived to see this legacy. He died with little recognition, his name known only in technical circles. Yet his creation spread across continents, survived 2 world wars, rebuilt nations, and quietly reshaped how humanity thinks about shelter. A mining engineer solved a military crisis, and in doing so, proved something timeless. When you truly understand the fundamentals, simplicity becomes unstoppable.